All right, welcome to CL06, the stimulation tutorial. So, if you made it this far, we're going to finally be doing stimulations. So, the little blue dots, the little blue lollipops, as we'll call them, are stimulations. And as you can see, the CL API provides precise control over the concurrent and complex stimulation of multiple channels. So being able to stimulate multiple channels to achieve a desired type of learning from the neurons or outcome. So, what does that mean? That means, how we read the spike patterns, the little green lollipops, against our stimulation patterns, and then quantify, the data that comes off of, it could potentially be, you can legitimately stimulate over here and be getting data from over here, because it is all one cohesive system. It is all one organoid. But it really will depend, on how, you read out your data. So if we come here, the channel cues, so each channel is independent and contains, each channel is independent and contains a queue of stimulation tasks. Each time a method like neuron stim is called, so neuron stim, the stimulation tasks are added to a queue for each channel passed to the methods. A stimulation task describes a lead time, a delay before the electrical stimulation event will start, the current duration, and the current and duration, so different. The current is the electrical flow, and the duration of up to 3 stimulation phases of alternating polarity, a trailing slash cooldown delay before another stimulation can begin. That is very, very important because you can exhaust these neurons. You need to give them time to rest and recuperate. And then an optional repeat counter to repeat the above for a fixed number of times. So stimulation tasks within a single channel are executed in the same order that they are added to the channel. One thing that I'm going to kind of make note on here is there is something that was discovered very early on in the CL1, and this is a tangent. It could be its own video. It's called the free energy principle. So in essence, when you're programming with neurons, they like to move from, chaotic like this, just random. They don't like that. They like, you know, one, one, two, three, two, one, two, three. They like a cadence that's predictable. So I've seen multiple different approaches taken here. I know that the Pong experiment had some elements of that. The Doom experiment, if you look at that code, also same type of thing, where um, if you want the neurons to learn something and be able to achieve a task, you have to move from a cadence of stimulation that is chaotic to a predictable one, which, the neurons then begin to imprint on that. So just a fun fact there, when you're going into this is, that's predictable is what they want, but sometimes you kind of do need to nudge them with the unpredictable, and they move from unpredictable to predictable. It's a quality you see all across the animal kingdom, all sorts of life in the world. That principle, free energy principle, is displayed. So I found other approaches too, but we'll just focus on what's been kind of published out there. Okay, so we've gone through what a stimulation task describes, but the stimulation task within a single channel, they're executed in the same order that they're applied to that channel and executed as fast as possible until the channel's queue is empty. So what does that mean? There's actually, a couple ways to be kind of approaching this. So this will show us, I believe, we end up with a little visualizer there like before. We import CL. Oh, wonderful. For this one, that is working very well. It wasn't working on a previous tutorial. Now, what we're going to do is create a common stim design, which is a symmetric biphasic pulse with 160 microseconds phase delay and 1 milliamp amplitude negative first. So, you can see the negative one first, the negative stimulation, and the positive stimulation in the stim design. So we're declaring stim design equals cl.stimdesign with cl.open as neurons. We're stimulating channel 1 right here with a, let me see, with a 25 hertz burst of 15x. The method returns immediately, but it does not wait for the stimulation to complete. So neurons.stim, one, stim design, and it follows this stim design and then goes and uses CL.burst design. So the stim design is different than the burst design. So the individual stimulation like that, how we define that stimulation is done right here. And then the cadence, so like I'm just clicking it right now, how many stimulations is defined by the burst. So we'll go ahead and we'll run this cell and you'll see it just goes, brrr, you have a ton of stimulations there. Um, I would not recommend doing this on an active channel, on a stimulation like that has that quick of a burst. Um, I have used that for, spike suppression. I have, to be very clear, that's typically from what I have found. Every culture is different, but I have worked with probably half a dozen different cultures at this point from Cortical Labs, and I can say that you really don't want to do that even on one channel. On all channels, you don't want to do that. It just causes problems. It's going to make your life harder. So you want to, you know, design smaller stimulations and really find and fit what works right for you in your use case. Because what I found is hey, some of the gaming applications that will make the neurons play a game, they're actually not good for like longer term data collection. They actually cause decline in the activity or unpredictable natures of the activity of the culture, and it makes it so you can't even collect good data. You basically kind of burn your culture out just to play a game or just to do a short task, which is like, considering the cost that goes into these, you do want longevity. You want something that's going to last more time, that's going to be meaningful to a longer scope mission. So just something to pay attention to. Now, channels one and two start stimulating at the same time almost. So that's important to note is that the act of adding stimulation to a channel's queue takes valuable microseconds. So by the time the above example has added stimulation to channel two, the stimulation in channel one is probably taking effect already. So another really important thing to note there is, just hey, like how you end up timing these things out and finding, those little baby nuances. They do make all the difference, So like just I found microseconds of latency, especially when you're recording data, it's very important, and it makes the difference between being able to design a pattern that does something really well, and doesn't do anything at all. So just something to note, but that's very specialized, what I just kind of said. So when we come down here and we use neurons.loop to see exactly when our stimulation occurs, channel two started at the same time as channel one. So this type of thing is important to really make sure that we start stimulating one frame after channel one, or we don't do that and we're able to do it closer together and have it be very highly predictable, which is very, very important to have it on the same frame when you're trying to make, data that's easily understood. Um, there are chances that you do want them to be frames apart, but, I can say this from other industries where latency is a big issue. Looking at, a lot of the stuff in blockchain and stuff, you are down to, milliseconds, and milliseconds do matter. So it's, when dealing with latency on device like this, kind of like that, you do have the tools to make a good stim plan where they start stimulating close enough, very, very close, and there's no drift. So just being very, very mindful of that. Now, when we look at the stim plan API, this allows you to create a plan for stimulating multiple channels at the same time. So it's like I was saying in the last video, CL05, when you're capturing raw data frame by frame, and you go and you make a stim plan like this, you really want to make sure that you're capturing data and be able to match it to your plan. So when you go and make a plan, you want that plan to coincide with the data that you collect so you can even do anything with it. So it's super, super important that, when we look at the stim plan API, you're importing the CL package. We have a first set of stims here that are happening on 1 and 2. So 1 and 2. And then we go to 9 and 10 right next to them. And then we have a common burst design down here. We have a burst that's happening on both of these stims. So, the cadence that's going to happen. This is the design of the stimulation. And when we come down to CL open as neurons, I'll just run this so we can just see those first two things kind of hit. So yeah, you see what I'm saying over here is, these ones were longer. So there was 20 and then 40 on, I think, set two. But with CL open as neurons, we had the channel 9 start the same time as channel 1. So these two started at the same time, and that's kind of the what we want to see here is just knowing it. And then if, we have the else statement down here. Let me see. Oh no, we have the frames here if it started after, so we know if it started at the same time and we know if it started after. So we're looking at our stim plan, we're repeating that same stim plan again, and then we're iterating through it with a for loop here in neurons.loop 20 stop after ticks. So to execute the plain stim plan just like neuron stim, and this method returns and does not wait for the stimulation to complete. And we're using the timestamps right here, again, to determine the first stim on each channel. So using that package that comes from CL, to time things out exactly as we want them to. Now, there are some cases, I think we've already kind of gone over that, but interrupting a stimulation is super interesting as well, because I'll just go out and say, like, hey, it's like what I was saying earlier, like, you could see these ones are being just absolutely slammed right now. And, interrupting a stimulation is important, and we'll go into why here. So if an ongoing stimulation as well as any cued stimulation on a set of channels needs to be stopped, you can use the neurons interrupt method. This will immediately stop any ongoing stimulation on the specific channels and clear any cues of pending stimulation tasks. To perform stimulation on the same set of channels immediately after interrupting, the neurons that interrupt and stim method is provided. So this is an example of how to interrupt the API to modulate the stim frequency on the set of channels. And you can kind of see, like, hey, when I do run this, which I will again, it goes from, it goes into this very quick cadence, very, very fast. And then, it begins to slow back down again. So what we need to look here and see though is basically the shared biphasic stim design in the channels. So 1, 2, 9, and 10. The tick rate is 50. The duration in seconds is 30. Max frequency is 4. Min frequency is 4. Max is 40. And pulses for burst is 100. So we're doing 100 bursts on these. And the sine wave modulation is 0.1. And the frequency modulation of sine wave right here is generated burst design based on a sine wave frequency modulation scheme. The sine wave oscillates between min frequency hertz and max frequency hertz. We can see it happening right there. And let's get into the actual neurons that interrupt, So down here with CL open as neurons, tick rates frame per second, initial timestamp is happening right there. So we're grabbing the initial timestamp and then handling with a for loop and interrupting here at the end, So after the loop is complete, we ensure that we stop the stimulation with a neurons that interrupt. Where I find this is the most useful in real code is when you're doing data analysis and you're seeing a decline on various channels. So it's like, hey, activity was great on channel 51, and now it looks like channel 53 and it's empty, or it looks like channel 52 and there's only, one every once in a while, one spike every once in a while. You can actually monitor that as you go, and using this to interrupt longer running processes that you might not be there you might not be looking over it. This is super important for culture, health, and safety. So just saying that that's probably the way you're going to end up using it. Um, is in that manner. But also, if, hey, let's say there's an action and the little guy in Doom is shooting a monster, and, you could also use it there where it's like, hey, if he's not shooting the monster right, stop what that's doing and start doing something, start doing a stimulation pattern that's predictable. So interrupt one that's chaotic, start one that's predictable. So again, that free energy principle, it's a good way to implement there um, on the fly, so when you're doing kind of the on the fly test time training style learning, you're doing online learning. This is really important because it helps you actually control those processes. Now, finally, for sync, we're going to run these pieces right here, these pieces of code. We will run, and you'll see an example one, neurons.sync. What we are able to do here is we've queued stimulations, and queuing works on a per channel basis. So if multiple channels have stims ending at different times, and the newly queued stim will kick off independently of the channel as soon as the previous finishes, rather than all starting together. That's where the sync API comes in. It lets you synchronize the start of the stimulation across multiple channels, no matter what's been already started in the stim queue. So as you can see, we already did run that. We ran number one, and then we will run number two here. And, we can see neurons.sync and then stimplan.sync. So you are syncing the neurons directly, channels 1 and 9 with a longer burst on channel 9 with the burst design. And then we're adding a single stim on channels 1 and 9. Note that this won't be synced, and simply add it to the end of each channel's burst. And then now we're calling sync to wait on all stims for the specified channels to complete, and then repeat the above stim. So this will occur synchronized after the last stim on channel 9. If we look at example 2, import CL, common stim design, and channel set. So more or less what we're seeing here is we're seeing stim design, CL stim design, and here we're using stimplan.sync. So it's similar to example one. So we're seeing a very similar thing here, but using a stim plan for more precise timing control. So this results in the following sequence where, we get 10 stims, one stim before sync and one stim after sync, 30 stims, one before sync and one after sync. And I'll just run one more time. So you could kind of visualize it, you could see it here, and that's what this produces here. And the syncing is again very, very useful for, when you discover a pattern potentially around a hub like 51 here, where you're getting results and you're getting spike activity that's controllable on 50, 42, 43. And you do want to sync that, or you want to sync something, I know I use this in some simulations for, making a better simulator of the CL1. So, there's endless possibilities. I could just, I gave some kind of, I give the Legos here, and it's kind of your job to take them and put them together. So, I hope you enjoyed this tutorial. I really appreciate your time and taking the time to learn all these things. And in the next one, we are going to be getting into building applications, and we've got a super fun demo for this as well.